Welcome back to Raw BM 101, an introduction to bioinstruments. In the last lecture, we talked about transducers. In this lecture, we will continue to look at various examples of transducers, how they work, and their applications. The first one we'll be talking about is strain gauge transducers. They measure the changes in the length of an object as a result of an applied force from the outside. This produces a resistance change in the object that is proportional to the fractional change in the length of the object, which is known as strain. The strain gauge has folded thin wires that are cemented to a semi-flexible backing material, as shown on the bottom. The two contacts, as shown below, are able to find the resistance between the 2 points, and this can help detect data based on the displacement. An unbounded strain gauge consists of multiple resistive wires stretched between a fixed and movable rigid flame, which was shown on the last slide, as well as here. The configuration is applied in blood pressure measurements, and an example of this can be shown below. Strain gauges have a variety of applications, including infant incubators, which are used in hospitals, hospital beds, as well used in hospitals, and dialysis equipment. Another application of strain gauge is intelligent prosthetics. For example, an intelligent knee can incorporate strain gauge circuits to measure forces in two directions. Forces detected by these circuits are used to control the position of the prosthetic during walking and running, leading to radical improvements in gait and stability of the patient. Another example of strain gauge is physiotherapy equipment. They're used to monitor patient work rates as part of post-operative rehabilitation processes. Robust and accurate load cells are continuously applied to monitor the force needed for the patient to exercise joints and limbs, and see how far they've gone in the rehabilitation process and what steps are further needed. The last example of strain gauge that we'll be talking over are infusion pumps. They provide pressure measurements to ensure blockages are detected. It is extremely imperative that the accuracy and integrity of the sensor is maintained, and it needs to work over the course of the device's lifetime. The next type of transducer that we'll be discussing is a capacitive transducer. Capacitance between two equal-sized parallel plates is affected by the difference in distance between them. Changing the separation distance, as shown below, between the plates can be used to measure capacitance. Capacitive transducers have a wide variety of uses, including measuring respiration or movement by having multiple transducers attached to a mat placed on a bed, or as a pressure transducer by attaching the movable plate to a thin diaphragm. They can also be used as advanced catheter systems that provide more useful data, and can also aid in the diagnosis of esophageal problems. Another critical capacitive transducer application is screening in clinical breast exams. A device called SureTouch can detect breast lumps, which could lead in the diagnosis of breast cancer. They also can control the amount of force when injecting insulin. The next example that we'll be discussing is airflow transducers. Pneumotactometers are used to monitor volume, flow, and breathing rates of patients on mechanical ventilators, as shown below. They work by creating slight pressure drops as air is passed through the tube, and the pressure drop is proportional to the air velocity. The most common type of airflow transducer is the flash neurotactometer. As mentioned before, they can be used for ventilators, but also for anesthesia machines. An accurate and constant supply of medical gases, mixed with an accurate concentration of anesthetic vapor, can deliver this mixture to the patient in a safe pressure and flow.